Good afternoon, everyone, and welcome to another session of Molex 3D's webinar series. My name is Srikar Valluri, and I'll be your host today. The topic for today's webinar is latest simulation technology for 3D warpage predictions. And I'm going to talk about how would you use simulations today in order to get good warpage predictions. What are some of the necessary things that you need to pay attention to, and how are the different ways in which you can use simulations to get your warpage predictions. Just a quick overview of what warpage is about, right? As almost everybody on the webinar here knows, warpage is nothing but uneven shrinkage in the part. Plastic material shrinks. When it doesn't shrink uniformly all across the part in all directions, that's when you can have warpage. Now, the factors that could cause warpage can be, they can range from what kind of geometry you have, what kind of material you're using, whether it has fillers in them or not, like glass fillers, carbon fillers, what sort of processing conditions are you using, what is your process like. So all of these and other factors can affect warpage. We, in essence, can break it down into four different aspects, if you will. Four different broad categories. One is your part geometry, your dimensions, thickness variations, etc. The next is your mold design. How is your runner layouts? What's your gating like? What is your cooling channel layout like? What sort of inserts do you have, etc. In terms of the material, then, like I already mentioned, what sort of a material is it? Is it easy to flow? Does it freeze faster? What sort of fillers does it have? Is it crystalline amorphous? And of course, when it comes to processing, what are your temperatures like? What are your times like? What is your transfer point? What are your pressures like, etc. So multiple things can obviously affect warpage. So in such a scenario, when you're trying to simulate your warpage prediction, then what are the factors that you would need to pay attention to in order to make sure that your simulation results, you can be quite confident on your simulation results, and you can be assured that they give you, at least they are reflective of what's going on in reality, right? From, again, a broad, high-level perspective, the workflow itself is pretty simple, straightforward, right? What you do is you collect the data, that's, your input data for the simulation. You set up your models, which we would categorize as pre-processing. In other words, you would do your meshing, you would assign your boundary conditions, you would assign the materials, processing conditions, etc. And then, of course, you would run the simulation, do your post-processing, and all that good stuff. So when you talk about collecting data, what are we really referring to? When you talk about collecting data, your part geometry, your CAD becomes very important, especially when you talk about CAD. Now, there are different versions or different ways in which you can look at CAD. CAD could be what the part designer sends off to the tooling people. But there is also what is called as tool CAD, which is the actual shape or dimensions that are used to cut the steel and what your actual tool is. So when you run a simulation, what stage are you running the simulation at will define what sort of CAD you would need to use. And you will find that that does have an impact on your shrink and warp predictions. Similarly, collecting data will include material properties, mold design, like I explained, and of course, your process sheet. So we can briefly look at each of these one by one. Now, when you talk about your part geometry, with your part CAD, ideally, if you're running the simulation after your tool design is done, you would want to include the shrinkage compensation or your mold compensation in the CAD that is used to run simulations. Otherwise, if you're using the ideal CAD from the part designers, it is not reflective of your actual mold CAD, which means your simulation results may not necessarily match up with reality when you look at your shrink and warp results. So then that becomes very important to take into account. When you talk about your material properties, the rheological properties of a material can vary, even though it is the same material supplier, even though it is a similar grade, even if the melt flow index is the same. The viscosity or the PVT behavior could be very different, which means the actual rheological properties of the material need to be captured as much as possible in the simulation. And they include your viscosity data, your PVT. In other words, how does your specific volume change with pressure and temperature? What are the mechanical properties? What is the viscoelastic behavior like for this material? And all of this is for the part. Now, let's say you have a part insert or a mold insert, like a core, in your tool that you want to include in the simulation. Is it a plastic core? Is it a metal core, like a regular steel? Or is it a special insert, like a mold star, beryllium copper, whatever? So then the actual properties, your thermal properties of those inserts also need to be taken into account, because that would affect how the temperature distribution in the tool is going to be like, and in turn, what your shrink and warp is going to be like. So all of these have a very direct effect on your result predictions. Now, if you're unable to find the exact grade for the material, then you would want to at least get in touch with the material supplier to see if they have that data. And if not, of course, there is always the option of using an alternative material in your simulations. As long as you are aware of what the differences are between the alternative material and the actual material grade, then you're okay. So take this as an example. You are looking at two materials from the same material supplier, and you do find a slight difference in viscosity and PVT also. So the blue curves indicate one material, the red curves indicate another material. Now, when simulations are run with both these material data, you find that the warpage predictions, even though the trend is the same, there is a difference in the magnitude. And these are the kind of things that can affect your overall accuracy of warp predictions when you compare with reality. Now, another aspect that you are taking into account is your cooling layout, part of your tool design. So let's say you are at a stage where you're running simulations when you don't have the actual tool design available yet. What do? It's not always necessary that you have your final tool design available when you're running simulations. So there is a very easy way of making sure your warp predictions are still reasonable and make sense, even though you don't have the actual tool design. So with simulations, it is very easy and straightforward to set up a generic cooling layout for your model, right? So once you set up a generic cooling layout, you can run what is a simulation without a cooling analysis. You can run a simulation with a cooling analysis, and you are able to, when you compare the results, you're able to immediately say how much of an impact is the heat accumulation happening, or in other words, the ability of the software to account for heat accumulation while versus not accounting for the heat accumulation. You're capturing that with such a simulation. And when you do such a comparison, you will also have a very good idea of what is the impact of such a heat accumulation. depending on the application, then you're able to make a decision about how big or small is the impact. So for example, what you're looking at here is a watt displacement, Y displacement, which you can see the axis here, what your Y displacement is. And you are comparing what your Y displacement is like when you run an ideal cool versus an actual real cool. So in this case, you do see that the part seems to be warping more when you run your actual real cool analysis. So that brings up the question, right? When you don't have a cooling channel design, you can run, you can put in a generic cooling layout, not unlike what you see in this picture here. You can have these lines both on the core and cavity side, and then you're running both two analyses, one without the cool, one with the cool, to get a relative idea of how sensitive is your warp result to your heat accumulation or lack thereof. And the other thing that this will help you identify is where are the hotspots for this design. And when you pass this on to your tooling engineers or suppliers, you were able to already point out where are those potential hotspots and where there needs to be good cooling. So this is another very important aspect and another consideration for getting good Warpage results. Now, going back one step, when you talk about your runner layouts or not using a runner layout in a simulation, you know, several times a lot of people, especially part designers, are nowadays trying to run simulations up front in the product life cycle, meaning when they are trying to run a simulation, they don't have any tooling design data available. So all they're doing is putting a gate on the part and running a quick simulation to see, you know, what the warp trend is like. But the runner layout, depending on your part geometry, of course, can have a substantial impact on what kind of warp you actually see in the part, because the runner layout will add to your packing effect on the part. And so what kind of pressures you actually see, what kind of pressure loss you see through the runner is better captured. Even if this is a generic runner layout, it'll still get you a much better idea of what your pressure requirements are and what your warp could be for this part, as opposed to not including the runner layout, as you can see in these two pictures. So what you see here are what your pressure distribution is like in your parts. And you can see how when you add the runner layout, obviously you have a bigger pressure drop in the runners, and you see what your overall pressure requirement is to fill that part. Now this will of course also lead to better packing effect and, you know, a closer warp result to reality, even though you're running these simulations upfront. And of course, when you talk about a process sheet, there are lots of information from the process sheet that can be obtained. And in a nutshell, basically, when you're trying, if you already have a process sheet available, if the part is already in production or prototyping, translating that process sheet to simulation would be very important. Otherwise, if you're just using generic data for processing conditions and then applying that, trying to compare that or correlate that with your prototype mold or with production, and if you're trying to troubleshoot something, that there would be a lot of mismatch. So having the right input data is very important in order to get better accuracy in your simulation results. But what next? Once you have all your input data lined up, what are the next steps that you take? Of course, the first step then would be to actually mesh your model in your pre-processing. Now, with MoldX 3D, the kind of meshing that you're able to do is what is called as a boundary layer mesh, which means at the boundary of when you look at the cross section of a part, you have these higher quality prism elements, and in the core you have these tetrahedron elements. So best practices for meshing are all explained during trainings and other webinars. So I'm not going to go into too many details about the best practices for meshing and etc. Right now. If you have any questions, feel free to talk to me later about that. But like I said, meshing would definitely be the first thing. Mesh accuracy, or a good mesh will play a role, will have an impact on the kind of accuracy you have in your results. Now, that was talking about the mesh for your part, right? What about your mesh layout for the runner? Now, your runner geometry and your runner mesh can be set up in a few different ways in the software. One is where you can have what is called as line-defined runners, which means you just draw center lines that define your runner layout and then attribute them as your runner system. Now, this would be very easy to draw, as well as the mesh that is generated is actually very, very good. The second option is you just bring in your runner geometry and have the software mesh that geometry. This is more useful when your gate or runner geometry is very complicated and it's not practical to define that with straight lines or center lines. Now, if let's say the third option is your gate geometry is complicated, but your overall main runner branch is not really that complicated, then you can use a combination of line defined and geometry. So that is also something that is very useful when setting up your meshing. And of course, the other important thing is to remember the refining of your mesh around your gating region, because that will have a big impact on all your flow rate profiles, velocity profiles through the gate, shear through the gate, pressure drops through the gate, etc. So, and of course, this will translate then to accuracy of your shrink and watt predictions or calculations. So having a good resolution of mesh at the gate through the cross section is very important. So to demonstrate this idea, what you're looking at here is a comparison of temperature distribution in your runner layout between a coarser mesh on the top and a finer or denser mesh on the bottom. And you can see how with the coarse mesh, the temperature prediction is lower than what you would expect to see with a finer mesh. And with the finer mesh, you are also able to very clearly see what your frozen layer looks like, or where you have these temperature regions, different regions in your temperature, your shear heating, etc. And of course, there can be cases where, depending again on your part geometry and other processing conditions, that can impact your warpage predictions. Like you see in this example, where the coarser mesh was actually giving you a different watt trend. And this can happen because the mesh was too coarse and it is not able to predict accurately what your temperature increase is and the subsequent freezing, shrinking of the part. And another thing when you talk about meshing and mesh resolution is it doesn't just, it's not just restricted to the part or the runner layout. Even your cooling channels and mold bays, depending on the kind of density you have in your, let's say, the mold base mesh, that will impact what sort of temperature distributions are predicted across your mold base. And this comparison is basically done with a very coarse mesh versus a much more dense mesh, right? and you are able to see the impact of that on where your hotspots are in the tool. So this is another example to demonstrate the importance of meshing for any simulation as such. Next, you're talking about your process settings, right? Again, what your times are, what your temperatures are, what your pressures are, etc. Anytime you have your process sheet, it can be translated very directly into the software, and you're able to specify all the things that all the knobs that you turn on the machine can be translated into simulation. And there is a very easy and direct way of doing that. Now, if you're running simulations, let's say, upfront in the design cycle, again, let's assume it's part designers who are running these simulations and they don't have a good idea of what are baseline process conditions to be used. So there is literature available online, and there are tips and tricks, rules of thumb that we provide. I know there have been other webinars talking about such tips and tricks to start off with baseline processing conditions. So depending on the kind of material you're using, the kind of injection volume, etc., you can start off, you can refer to such literature and start off with good baseline processing conditions. And of course, depending on the kind of process you input, that will impact again what your results are. So in this example, you're looking at two different flow rate profiles. Now, the average flow rate profile, the average flow rate in this case is still the same between the two cases. But in the first case, you have a much slower flow rate to begin with, and then there is a ramp up to the flow rate. Towards the end of fill, again, it drops down. While in the second case, it's all a uniform flow rate. This does directly translate to how it affects your screw pressure profile. And of course, screw pressure, your overall injection pressure, packing pressure, they get impacted, or they impact what your packing effect is going to be like and what your overall walk is going to be like. So again, talking about the workflow that you would follow in order to enable good warpage or good and accurate warpage results. First step would be to verify the data, your input data, including your CAD, including your tool CAD, including your material, process conditions, etc. And then, of course, when you talk about pre-processing, you're talking about your meshing, your process settings, your computation parameters in the software, etc. And then finally, you're running your simulation depending on what you're looking for, depending again on what stage, at what stage in the product life cycle you're running your simulation. That will define what is your analysis sequence going to be like. And of course, you're able to compare results between different processes, different materials, different geometries, etc. With that being said, I'd like to quickly go over a few case studies to give you an idea of how simulation can really impact your watt predictions. So the first case study, this is a thin wall. The nominal thickness was pretty small for this. This was a laptop cover, a back cover of the laptop. And what they were looking at was quite significant warpage because they had thickness variation, right? It was not a uniform thickness. In their original design, they basically had two materials again, as you can see here, with copper section placed on top and your plastic. You can see what the thickness of the plastic is and what the thickness of the copper is here. And in the revised design, they were looking to replace the copper with aluminum and also increase the overall thickness of aluminum. To them, the advantages were better strength, ease of manufacturing, etc. can see what the overall tool design was like here, what the runner layout was, hot to cold, and then what the cooling channel layout was. And in terms of flow progression, you are able to see from both the bottom as well as the top side how your melt front progression is like, how it is flowing over the aluminum, and then, like I said previously, their goal was to reduce warpage. The original design, it had significant warpage, and you can look at the shape of warpage that was happening in the Z direction or out of plane direction, which was not at all acceptable to them. And what they realized also is that the main cause of the warpage was thermal effects. So the shrinkage effect. Thermal effect, there was a thermal effect to the warpage, but it wasn't the biggest factor. Shrinkage, what was causing the biggest warp in the part, or effect of the shrink. So then, what they went about doing was consider molding this with glass fiber, right? Different material and different percentage of fiber filler. The original material was a SABIC. The new materials that they tried out were with different percentages of fiber, right? 10 and 40. And in this case, you already see with 10% glass, there is a significant reduction in warpage. And of course, with the higher percentage of glass, the reduction in warp was even better. And so in this case, compared to what they had before, they almost nearly had a flat part. And this was what they went with, because this was well within their tolerance. So this is an example, one example of how you can use simulations to not only verify your design, but also verify the impact of a material or changing a material on your part quality. The next case study is talking about a slightly different sort of an issue. Again, in this case also, they had an insert, they had quite a big thickness variation in their part. The material that was used was a PVC, and this was basically a side window encapsulation. Now, they had three different inserts in this assembly, right? They had transparent glass, they had aluminum insert, GRC, etc. And this is giving you an idea of what the actual part looks like. But when you look at the cross section of the geometry, you can see where they have a very thick section that was causing a big hotspot in their model, and it was causing unacceptable warpage for them. So you can see in the simulation, you're able to identify where that hotspot is. And this was basically causing all the issue in the warp. The biggest effect here was the thermal effect. And when you look at the warp, it was a pretty significant warp for them. They needed to reduce this. So the thing that they wanted to try was coating out the part there, right? Adding ABS insert. And by doing that, they're basically not compromising on the stiffness of the part, because that was a big concern to them. And when they model that in, including the new insert now, and run a simulation, you are able to see how your hotspot is taken care of. The modified design does a better job of reducing the hotspot in that area, where you had a big region of molten material before. That was no longer the case, and that helped improve the overall warp also, as you can see from this animation and the result. So this is another example of how simulation can be used to identify the cause and effect, right? What was causing the warpage in this case, and what needed to be done to reduce the warp. Now, the next case is an interesting case, actually. In this scenario, they were trying to switch from metal to plastic. Now, of course, again, they were dealing with thick walls, non-uniform thicknesses, etc. And what they were trying to do was do a reverse warpage study to see how could they use simulation to optimize their overall design, right? So the material that was used in this case was a POM, and the redesign of the mold was done by a workflow they followed. The workflow they followed was they took the initial baseline design and conditions, they ran a simulation, and once they had the warp result, they exported out the reverse of that warp shape, took it back to CAD, and overlaid it with their original design to look at what were those areas of deviation, where was it okay, where was it deviating a lot more. And so then they went about doing an iterative process. They had their nominal CAD, and then they were comparing what the original CAD would look like versus the nominal CAD, meaning the tool CAD versus the nominal CAD. And they were also trying a couple different things, single melt entrance, two melt entrances, but they were all the way through overlaying, comparing the scanned models with the nominal CAD in order to improve the overall design. So what you see here is an overlay of the nominal CAD with the original tool CAD. One melt entrance, two melt entrances, and then the final part that was molded after cavity redesign. So what this tells you is, how to read this is, everything that's green, meaning everything that's at zero, is basically in almost perfect correlation with the ideal CAD or the original CAD. And then anything that's away from green is deviating, showing warpage. Now, in this case, besides doing the warpage studies, they were also studying, weakness or failure of the part. And when they looked at scanned results of the part, they were able to see where they had those air traps or voids in the core of the part. When they cut the sample, a layer of the part, you can see where you have your voids, and these are indicated also by where you have your higher temperatures from the simulation, meaning indicative of hotspots, indicative of higher shrinkage, and occurrence of shrinkage voids. So this was a very interesting case study that was done by one of the companies. Now, the final case study that I quickly want to share with you is, it's less of a case study and more of a workflow as to how would you go about trying to apply shrinkage compensation to your design, and get a good design out of your simulation process. So let's say you start off with your target design, which is A here, which is represented by your dotted line. You go ahead and run a simulation on your target design. Now, the simulation will give you an idea of what is your shrink like, what is your warp like overall in the part. And that is the B, or simulate target design. Now, once that is done, you can export out the reverse of this deformation. You can export out the deformed model and take it to CAD, or you can also export out the reverse of the deformation and overlay it with CAD to look at what the deviation is like. And once that is done, you're then able to apply the compensation to your CAD and run another iteration on that design in order to see how your part is coming out to be after applying that compensation. Now, the software also allows you to apply what is called as a shrinkage. There is a tool called a shrinkage compensation tool. Software gives you an idea of what your linear shrinkage is like in that part based on all the other factors taken into account. And that linear shrinkage can be plugged in into this tool to then look at what the actual warp is for this part. So this is a workflow that you would follow from a simulation in order to identify, what is your warp like? What sort of compensation would you need to apply in order to get good tooling CAD, to go cut steel. With that said, this is the last slide that I have showing what is the interface like when you try to apply your shrinkage compensation, when you're trying to export out your deformed model after the compensation, etc. So that brings me to the end of my presentation.